everyone. I Pritha Gupta welcome you all to the Swayam online course on basic principles of energy management and energy audit. In this course, I will be dealing with the topic renewable energy sources. In continuation with the series, today we are going to learn about the wave energy, tidal energy and geothermal energy. Differential warming of the earth causes pressure differences in the atmosphere, which generate winds. As winds move across the surface of open bodies of water, they transfer some of their energy to the water and create waves. Wave energy, also known as ocean wave energy, is another type of ocean based renewable energy source that uses the power of the waves to generate electricity. Unlike tidal energy, which uses the ebb and flow of the tides, wave energy uses the vertical movement of the surface water that produces tidal waves. Wave power converts the periodic up and down movement of the waves of the ocean into electricity by placing equipment on the surface of the oceans that captures the energy produced by the wave movement and converts this mechanical energy into electrical power. Wave energy is actually a concentrated form of solar power generated by the action of the wind blowing across the surface of the water of the ocean, which can then be used as a renewable source of energy. A few factors determine how strong an individual wave will be. These include: number 1, speed of wind. The faster the wind is travelling, the bigger a wave will be. Time of wind. The wave will get larger the longer the length of the time the wind is hitting it. Distance of wind. The farther the wind travels against the wave, known as fetch, the bigger it will be. Not all coastal areas are suitable for wave energy extraction. Regions with consistent and strong wave patterns are ideal. Therefore, wave energy potential assessments are conducted to identify suitable locations for wave energy installations. Several technologies are used to harness wave energy, each with its own unique approach to capturing the energy from the ocean waves. Here are some of the key wave energy conversion technologies. Number 1, point absorbers. Point absorbers are floating structures that move with the up and down motion of waves. They consist of buoyant platforms connected to generators. As waves pass beneath the platform, it rises and falls, causing the platform to move. This motion is used to drive a generator which converts the mechanical energy into electricity. Point absorbers are relatively simple in design and can be used in wide range of wave conditions. Second, attenuators. Attenuators are long floating structures with multiple joints or sections. These sections flex and move with the waves. As waves pass through the attenuator structure, the relative motion between the sections drives hydraulic pumps or other mechanisms which in turn generate electricity. Attenuators can capture energy from both the vertical and horizontal motion of waves, making them efficient in a variety of wave conditions. Third, terminators. Terminators are similar to attenuators but are oriented perpendicular to the direction of wave propagation. As wave approach the terminator, it moves up and down with the waves, generating hydraulic pressure that is converted to electricity. Terminators are effective in capturing energy from waves approaching from different directions, making them adaptable to changing wave patterns. Fourth, oscillating water columns. Oscillating water columns consist of partially submerged chambers with an opening below sea level and a roof above it. Waves entering the chamber causes the water level to rise and fall, creating variations in air pressure. These pressure fluctuations drive a turbine connected to a generator producing electricity. Oscillating wave chambers are known for their reliability and relatively simple design. Tapered channel systems. These systems use a tapered channel that narrows as it extends inland from the shoreline. As the wave propagates into the channel, they increase in height due to narrowing of the channel. This increase in wave height can drive turbines at the channel's end, generating electricity. Tapered channel systems can concentrate wave energy, potentially increasing efficiency. Now, what are the advantages of wave energy? Renewable and sustainable. Wave energy is a renewable source as long as the Earth's oceans exist, which makes it a sustainable source of power generation. Predictable and consistent. Ocean waves are relatively predictable as they are driven by factors such as wind speed and duration. This predictability allows for efficient energy generation and planning. Low greenhouse gas emissions. Wave energy generation produces very low greenhouse gas emissions compared to fossil fuels, making it an environmentally friendly energy source. Stable energy supply. Unlike some other renewable energy sources like solar and wind, wave energy is not dependent on weather conditions. It can provide a more stable and continuous power supply. High energy density. The energy density of ocean waves is relatively high compared to other renewable sources, allowing for the generation of significant amounts of electricity. Minimal land use. Wave energy installations typically occupy relatively small areas in the ocean, leaving coastal land available for other uses. Disadvantages of wave energy. Environmental impact. The installation and operation of wave energy devices can have environmental impacts on marine ecosystems. These impacts may include disruption to local habits, changes in water flow patterns and interference with marine life. Second, high capital cost. Energy can be expensive and the initial capital costs are relatively high. This can make wave energy less economically competitive compared to other energy sources. Maintenance and durability. Wave energy devices must withstand harsh marine conditions, which can lead to maintenance challenges and a shorter lifespan compared to other infrastructure. Variability in wave energy. Wave energy availability can vary significantly based on geographical locations and weather conditions. This variability can affect the reliability of wave energy and generation. Infrastructure and grid integration. Building the necessary infrastructure and integration wave energy into existing electrical grids can be complex and costly. Limited geographic range. Not all coastal areas are suitable for wave energy extraction, limiting its geographical availability. In summary, wave energy has the potential to be a valuable contributor to the wave energy mix, but it faces challenges related to cost, environmental impact and infrastructure development. Continued research and development efforts aim to address these challenges and make wave energy more competitive and sustainable. Tides are the waves which are caused primarily by the gravitational pull of the moon and to a lesser extent by the sun. Tidal energy, also known as tidal power, is a form of renewable energy that harnesses the rise and fall of the ocean tides caused due to the gravitational forces between the earth, the moon and the sun to generate electricity. Here is a simplified explanation of how tide occurs. Number 1, gravitational pull of the moon. The moon's gravitational force attracts Earth's water, creating a bulge of water on the side of the earth facing the moon. This bulge is the high tide. Second, gravitational pull of the sun. The sun also exerts a gravitational force on Earth's water, creating another bulge, though it is smaller. than the one caused by the moon. This bulge is a secondary influence and is known as a solar tide. Third, Earth's rotation. As Earth rotates on its axis, locations on the Earth's surface move through the two tidal bulges. This movement results in two high tides and two low tides occurring roughly every 24 hours and 50 minutes. This is because it takes slightly longer for a specific location on Earth to rotate from one tidal bulge to the next due to moon's orbital motion. Tides are also influenced by the relative positions of the moon and the sun. Spring tides and neap tides are the two types of tidal patterns that occur as a result of the gravitational interactions between the moon, the sun and Earth. These tidal patterns create variations in the height of ocean tides throughout the lunar month. Here is an explanation of both. Number 1, spring tides. Spring tides occur during the full moon and new moon phases, when the sun, earth and moon are aligned in a straight line. During a spring tide, the gravitational forces of both the moon and the sun reinforce each other. This leads to higher high tides and lower low tides than usual. Spring tides have nothing to do with the season spring. The term spring is derived from the Old English word springen, which means to rise or to leap up, signifying the rise of the tide. Spring tides are characterized by a greater tidal range, making the difference between the high and low tide more pronounced. Neap tides. Neap tides occur during the first and third quarters of the lunar month when the sun, earth and moon form a right angle, a 90-degree angle to each other. During neap tides, the gravitational forces of the moon and the sun partially counteract each other. This results in lower high tides and higher low tides than average. Neap tides have a smaller tidal range compared to spring tides, meaning the difference between high and low tide is less noticeable. It's important to note that while the moon and sun are the primary drivers of tides on Earth, other factors such as Earth's elliptical orbit around the sun and inclination of the moon's orbit can also influence the exact timing and intensity of tides. There are several methods for capturing tidal energy, but the most common approach involves using underwater turbines. Here is how tidal energy generation works. Tidal energy is generated by the difference in water levels between high tide and low tide, known as the tidal range. The greater the tidal range, the more potential energy is available for conversion into electricity. The primary components of a tidal power plant are underwater turbines or underwater windmill-like structures known as tidal turbines. These turbines are positioned on the seabed or anchored to the ocean floor in the path of the tidal flow. As the tide comes in and goes out, the water flows over the tidal turbines. The movement of water causes the turbines to rotate. Some tidal power plants use vertical axis turbines while others use horizontal axis turbines, similar in design to underwater wind turbines. The rotation of the tidal turbines drives generators which are typically located inside a housing or a nacelle attached to the turbine. The generators convert the mechanical energy produced by the rotating turbines into electrical energy. The different types of tidal power plants includes: number 1, tidal stream systems. These systems capture the kinetic energy of the moving water and are positioned in the path of strong tidal currents. They resemble underwater wind turbines and use the rotational motion of the blades to generate electricity. Second, tidal rain systems. Tidal rain systems capture energy from the difference in water levels between the high and low tides. They include tidal barrages, tidal lagoons and tidal fences. These systems use gates and turbines to control the flow of water and generate electricity as it passes through. Third, dynamic tidal power. Dynamic tidal power is an emerging concept that aims to capture energy from the movement of water between two adjacent bodies of water with different tidal levels, such as a sea and an estuary. It involves the construction of a barrier or dam to create a high difference for energy generation. Tidal energy is considered as a reliable and predictable source of renewable energy, as tides follow a regular and known pattern. However, it has some challenges, including the limited number of suitable locations, the high initial construction cost and potential environmental impact on local ecosystems, and fish migration patterns. Researchers and engineers are continually working to address these challenges and improve the efficiency of tidal energy systems. Geothermal energy. Geothermal energy, a form of renewable energy, taps into the Earth's vast reservoir of thermal energy, which is the result of the natural decay of radioactive elements in the Earth's core. Geothermal energy harnesses the Earth's natural heat emanating from the beneath its surface, offering a consistent and reliable source of power. This energy source, deeply rooted in the Earth's geology and driven by the planet's internal heat, holds the potential to play a pivotal role in our quest for a greener and more sustainable future. The topmost part of the Earth is a crust. Below the crust of the Earth is a layer called mantle. The top layer of the mantle is a hot liquid rock called magma. The crust of the Earth floats on this liquid magma mantle. When the magma breaks through the surface of the Earth in a volcano, it is called lava. For every 100 meters you go below the ground, the temperature of the rock increases about 3 degrees Celsius. So, at a depth of about 3000 meters below ground, the temperature of the rock would be hot enough to boil water. Deep under the surface, water sometimes makes its way close to hot rock and turns into boiling hot water or into steam. The hot water can reach temperatures of more than 148 degrees Celsius. When this hot water comes through a crack in the earth, it is known as hot spring. Some of the areas have so much steam and hot water no fuel is burned to heat water into steam. Geothermal energy resources are found beneath the Earth's surface and they vary in terms of temperature, depth and accessibility. The availability of geothermal resources depends on the geological characteristics of a particular region. Here are the primary types of geothermal resources are: number 1, hydrothermal resources. These are the most common and widely developed geothermal resources. They consist of underground reservoirs of hot water or steam. The temperature of the reservoirs can vary, but is typically high enough for direct use applications or electricity generations. Wells are drilled to access the hot water or steam, which can be used for heating, electricity generation and other industrial purposes. Second, geopressured resources. These resources are found in sedimentary basins with high levels of pressure and temperature. They typically contain a hot brine, a mixture of salt water and geothermal fluid. While the temperatures are high, the resources is often used under significant pressure. Geothermal pressured resources can be used for electricity generation and direct heating. Third, hot dry rock. Hot dry rock geothermal energy is derived from extremely hot rocks found at the depths of several kilometers below the Earth's surface. Water is pumped into these rocks through the injection wells and heat is extracted through production wells. This method is still in the experimental and development stages and required advanced drilling technology. Fourth, magma resources. These systems are associated with volcanic regions and are characterized by the presence of molten magma. They can have extremely high temperatures and are a potential source of geothermal energy, but they are also challenging to access due to the harsh conditions. Fifth, low temperature geothermal resources. Some geothermal resources have lower temperatures and are suitable for direct heating and cooling applications such as district heating, greenhouse heating and spas. These resources are more widespread but require heat pumps or other technologies to raise the temperature for practical use. The availability of these geothermal resources varies by region, with countries located along tectonic plate boundaries like Iceland, the United States and parts of Europe and Asia having more accessible and developed geothermal energy resources. Harnessing geothermal energy often requires drilling wells to access the heat source, which can be expensive and technically challenging. However, the development of geothermal technology continues to expand the reach and utilization of these valuable renewable energy resource. There are several different types of geothermal power plants, each designed to harness the Earth's heat and convert it into electricity. These power plants vary in their technology, operational principles and suitability for specific geothermal resources. Here are the main types. Number 1, dry steam power plants. Dry steam power plants are the simplest type of geothermal power plants. They use high temperature steam from underground reservoirs to turn turbines and generate electricity. Steam is extracted directly from geothermal wells and channeled to a turbine which drives a generator to produce electricity. Dry steam power plants require geothermal reservoirs with a high pressure steam source. They are most effective in areas with ample high temperature steam. Second, flash steam power plants. Flash steam power plants are the most common type of geothermal power plants globally. They utilize high pressure, high temperature, hot water from underground reservoirs to produce steam and generate electricity. Hot water is brought into the surface and rapidly depressurized in a separator, which causes it to boil and produce steam. The steam then drives a turbine generator system. Flash steam power plants are suitable for reservoirs with high temperature water but may not require the presence of naturally occurring steam. Third, binary cycle power plants. Binary cycle power plants are designed to harness moderate temperature geothermal resources by using a secondary working fluid with a lower boiling point than water. Hot geothermal water is passed through a heat exchanger to transfer its heat to the secondary working fluid, example isobutane or isopentane, which vaporizes and drives a turbine connected to a generator. Binary cycle power plants are versatile and can be used with lower temperature geothermal resources, making them suitable for a broader range of geothermal sites. Fourth, combined cycle power plants. Combined cycle power plants combine elements of both binary cycle and flash steam technologies. They can efficiently utilize higher temperature geothermal resources. High temperature geothermal fluid is first used to generate electricity via flash steam. The remaining lower temperature fluid is then used to heat a secondary working fluid in a binary cycle for additional electricity generation. Combined cycle power plants are effective in areas with geothermal reservoirs that have a wide range of temperature gradients. The choice of geothermal power plant depends on the temperature and composition of the geothermal resource as well as the specific conditions of the site. Developers select the most suitable technology to maximize the efficiency and productivity of the power generation process. So, with this we came to an end of today's lecture. Along with the completion of the lecture series of course Renewable Energy Source. Thank you for your patience and hope that this lecture series will help you to solve all your queries regarding the basics of renewable energy sources in near future. All the best. Thank you.